In section 13.3, we're going to focus on the dot product between vectors. So when we talk about the dot product, they're used to determine either an angle between two vectors or to calculate projections. In this box, we're going to look at the definition of dot products. So if you have two vectors, u and v, their dot product is the number. So that means it's a scalar, it's not a vector. And we write u dot v, which would be equal to the product of the magnitudes of the two vectors times cosine of theta. So theta is going to be the angle between the two vectors. And here we're only concerned with theta from 0 to pi. So if u or v is 0, then the dot product is 0, and theta is undefined. So we can take this equation and also write it in alternate ways. So oftentimes if we're trying to find the angle, then we would use cosine of theta is equal to the dot product divided by the product of the magnitudes. Sometimes we're trying to solve for the angle, and then we would just take cosine on both sides. So we're going to look at the four possibilities of theta with our vector u and v. In this first diagram, let's say we have some vector u. And then we have a vector v that's going in the same direction, and they have the same tail. So the angle between these two is going to be 0. Now the next case, and also notice that these vectors are parallel. So the next case that we're going to look at is if we have some vector u and a vector v, where the angle theta between them is some acute angle between 0 and pi over 2. So in this case, our cosine is going to be positive, and then our dot product will also be positive. The third case we're going to look at is if u and v are actually perpendicular, and they're going to be perpendicular if the angle theta formed is a right angle. So in that case, theta is going to be pi over 2 or 90 degrees. Because cosine of theta is going to be 0, the dot product will also be 0. So we do say perpendicular when we have a right angle, but we also say orthogonal and oftentimes we'll also use the word normal. They all mean the same thing. It means there's a 90-degree angle that's formed, or an angle of pi over 2. The next example would be if there's an obtuse angle between our two angles u and v. So theta is between pi over 2 and pi. And there's a cat outside my office. Don't know if you can hear the howling. So in that case, cosine is going to be negative, which means the dot product will also be negative because the magnitudes are always positive. So the last example would be where we have u and we have v going in the opposite directions. So the angle theta that's formed between u and v would be pi. And note that in this case, these vectors are also parallel. So to sum up these properties, and I apologize again. So if theta is pi, and the vectors are parallel, but they're going in the opposite directions, notice that cosine of pi is -1, so the dot product is going to be negative. So summing up the properties, u and v are parallel, and that would be when theta is 0 or theta is pi, if and only if their dot product is plus or minus the product of their magnitudes. U and v are orthogonal, or perpendicular, or normal, and that happens when theta is pi over 2, if and only if the dot product is equal to 0. And then we have a property that says the 0 vector is orthogonal to all vectors. And that's because when you take the 0 vector and you dot it with any vector, it's equal to 0. In example 1, we're going to sketch some vectors and we're going to compute the dot product. We're going to compute it using that definition. Now, that definition is oftentimes not very usable, and we'll find this a lot in mathematics, that some definitions, we may want to use them in a different way. So first we're going to use the definition in example 1. We'll look at A. We want to sketch these vectors, and this is in three-dimensional space. So I have my x, y, and z axes. If I look at my vector u, it's going to have a head of 2, 2, 0. So 2 on the x, 2 on the y, and 0. So this would be my u. My vector v is 0, 0, 3, so that's just up 3 on the z-axis. Okay, so if we were going to compute the dot product of u with v, it's supposed to be equal to the magnitude of u, and the magnitude of u is the square root of 2 squared plus 2 squared. Okay, and then we're going to multiply that by the magnitude of v, which would be the square root of 3 squared, or 9. All right, so if we did, and then that's cosine of theta. What is theta, though? Well, you have to imagine this. In two-dimensional space, u is halfway between x and y. And then, or v, sorry. Ooh, did I write? U here, this should be v. And then v is going up in the z direction. So the angle between them is actually pi over 2. Which means their dot product is 0. It's kind of tricky using the definition. Let's look at B, and then we'll look at another way to compute dot products. So B, we just have vectors in two-dimensional space. Oh, that's going to be nicer. I have u as the vector 1, 1. And v is the vector 1, 0. And again, this is just a sketch. So when we compute theta, theta is the angle between u and v, and it's a 45-degree angle, which would be pi over 4. So you could use either one. And the dot product of u with v is going to be equal to the magnitude of u is going to be square root of 2 times the magnitude of v, which is the square root of 1, times cosine of pi over 4. and that would be square root 2 over 2. So this is going to be the square root 2 times the square root 2 over 2, and that's 1. Okay, so what we're going to do next is we're going to look at an easier way to compute dot products instead of actually needing to compute theta. Now, using the definition is fine if you already have theta, but if you don't have theta, it might be nicer to use this formula, and it's a very simple formula. It says if you have any vectors u and v, then their dot product is multiply component-wise, so u sub 1 times v sub 1 plus u sub 2 v sub 2 plus u sub 3 v sub 3. So multiply, add, multiply, add, multiply. So we're going to verify example 1 and see if we still get 0. So if you recall, we had two vectors, 2, 2, 0, and the other vector we had was 0, 0, 3. So by the dot products, we would multiply 2 times 0, which is 0, plus 2 times 0, which is 0, plus 0 times 3, which is 0. And it checks out. All right, let's try the other one. So our other example, so this was example A, right, in example 1. And then we had example B. Example B, we had the vector 1, comma 1, and the other vector was 1, 0. So looking at the dot product of these two, that would be equal to 1 times 1, which is 1, plus 1 times 0, which is 0. And we have 1, which is what we had when we actually found the angle and computed the dot product using the formal definition. And you could use either one of these. Right? Typically, if you don't have the angle, the multiply, add, and so on is the easier one to use. Example 3 says find the angle between these two vectors u and v. So if I'm supposed to find an angle, then that tells me I'm going to use the definition of the dot product. And I'm going to use that cosine of theta is equal to the dot product of u with v, and u is a square root of 3, 0, 1, dotted with 1, comma 2, comma 0, over their magnitudes, and then I'm going to multiply the magnitudes. Okay, so this is from the definition. So cosine of theta is going to be, their dot products would be multiply plus multiply plus multiply over magnitude of square root of 3 squared, which would be 3, plus 1 squared, which would be 1. I have square root of 4 times 1 plus 4, that would be square root of 5. It looks like we have the square root of 3 over 2 times the square root of 5. And normally what we would do at this point is to rationalize. But this is not going to be a cosine of theta that I recognize, say, on my unit circle. So I'm actually going to look at theta equal to cosine inverse. And I'm not going to bother to rationalize this because I'm just going to plug this into my calculator since this is not a known value from our unit circle. And if I were to plug this in and look at radians, I get about 1.17 radians. And we were talking about radians basically this whole time, but you may also want to write an answer in degrees if it's appropriate. So you can either change the mode on your calculator or you can do your conversion to degrees. All right. So another thing we can do with dot products is we can determine whether vectors are parallel, orthogonal, or neither by looking at their dot products. Because remember, if vectors are parallel, then their dot products would be plus or minus their magnitude. Okay, so parallel vectors have theta of 0 or theta of pi. And then orthogonal vectors, their dot product is 0. So I think checking to see if they're orthogonal, that's usually the easiest thing to do first. So I'm going to take the dot product of the two vectors. And I'll get -1 plus 0 plus 2. So that would be a +1. Okay, which tells me they're not orthogonal. Remember, orthogonal means perpendicular, normal. That means that when you take the dot product, you get 0. All right. So let's see if they're parallel. So vectors are parallel if the dot product is equal to plus or minus the magnitude of the product of the vectors. So all we have to do is compute these separately. The dot product, we already found that that was 1. Now when I compute the product of the magnitude, it'll be plus or minus. The magnitude of u is going to be the square root of 5. The magnitude of v is 1 plus 4 plus 1, so the square root of 6. So notice that this is plus or minus the square root of 30. And that's not equal to 1. So I also found that these are not parallel. So the answer is neither. These vectors are neither orthogonal nor parallel. In this box, we're just going to look at some of the properties of dot products. So the order does not matter. You can do u dot v or v dot u, and you end up with the same number because remember, we're multiplying and adding, and those properties are all commutative. If you take the dot product of two vectors and you multiply it by some scalar c, well, instead of distributing the c to all the components, you can just distribute c to one vector and then dot. Or you could distribute it to the other vector and then dot. Okay, so it's not the same as multiplying a vector by a scalar c, not necessarily, right? And then if you take a vector u and you dot it with two vectors that you're adding together, then you can distribute the dot product to have u dot v plus u dot w. Something that comes up quite a bit in physics, engineering courses, and in this course as well, is this idea of a projection. Okay, so we're going to look at projection vectors next. And when we talk about projection vectors, what we're going to do is we're going to say, okay, well, let's say we have this vector u. And imagine that we're shining this light on u. And we're going to get a shadow of u onto some vector v. Okay. So the shadow of u will create a vector that is parallel to our vector v. And there's going to be 3 different cases, okay, depending on our vector u. If the angle between u and v is an acute angle, where v is actually longer than u, then the first diagram would be what the projection would look like. So that's actually the same as this second diagram as well. We have this u, we have our vector v, and then we have this projection of u onto v. So that would be that shadow. Again, that's when we have an acute angle theta. So theta is between 0 and pi over 2. So a right angle is formed on the same side of v. If our vector, or our angle, is between pi over 2 and pi, what happens when we have this shadow is that the shadow of u is actually going in the opposite direction of v. So the right angle that is formed is opposite of where our vector v is. So the vector v is just giving us parallel, right? Our projection vector is written as the projection of u onto v. So v is the subscript, and v actually doesn't matter. We only need v for direction. We don't really care about the length of v. It's more important that we look at u. So these are all projection of u onto our vector v. Algebraically, when we figure out the projection vector, it is going to be a vector. Okay? There's a bunch of different formulas that you could use, and it depends on what you have or what you're comfortable using. The first one would be you would take the magnitude of u, because our new vector is going to have a length similar to that of u. And then we're going to times it by a cosine of theta, and then multiply that by the unit vector v. So that would be v divided by its magnitude. And in all of these cases, we're just using v as a unit vector just to simplify our computations. We didn't have to. We could use any length v, because if you notice in the diagram, we only need v for direction, not for v's length, okay, or magnitude. So the other thing we can do is if we have our scalar, so a scalar is of our vector u onto v is actually in the bottom here. It's going to be the scalar component of u in the direction of v, and it's going to be the magnitude of u times cosine of theta. It's actually a number. It's not a vector. Okay? So the scalar component is a number, and you would just multiply that by v divided by its magnitude. Another formula you could use, remember these are all equal, is you can dot u and v divided by dot v and v, and then multiply that by the vector v. So that would give you a scalar that you would multiply v by. Or you could take the dot of u and v, and this is exactly the same as a previous one. Look at it as magnitude squared times the vector v. So our scalar is magnitude of u times cosine of theta if you have the angle theta. If you don't, the scalar is going to be the dot of u times u, I say times, but I mean u dot v, divided by the magnitude of v. So again, all of these are equal, and you're free to use whatever you want to compute your projection vector. All right, so let's do some computations. Let's find the scalar component. So that would be of u with respect to v. So our u is 112 So it's u onto v. V is negative 2, 3, 1. So I'm going to use u dot v divided by the magnitude of v because I don't have theta and I don't want to figure it out. So this is what I'm going to use for my scalar, u dot v divided by the magnitude of v, which would be negative 2 plus 3 plus 2 in the numerator, and then our magnitude of v should be 4 plus 9 plus 1. Right, so remember this is going to be just some number. It turns out to be 3 over the square root of 14, which I am not going to rationalize. I'll just leave that scalar component as 3 square root of 14 over square root of 14. Okay, so let's find both now. In example 6, we have u is 1, 2, v is 2, 5. We want to find both the scalar and vector projections of u. So first of all, I'm going to do the scalar, because once I have the scalar, it's really easy to find the projection vector. So remember scalar, S-C-A-L. Okay. V is the subscript. It's u onto v. That's going to be equal to u dot v over magnitude of v. And then that would be 2 plus 10 over square root of 4 plus 25. All right, so my scalar is going to be 12 over the square root of 29. So I found the scalar. Now I'm going to find the projection vector, okay, of u onto v. So remember, I can use the scalar for that, which I already found. So I'm going to use the formula that takes a scalar, and then I'm going to look at my times my vector v over its magnitude. So there's my scalar times the vector v over the magnitude of vector v, which would be 29, because we already figured that out. So my projection vector is going to be 12 over 29 times this vector 2, 5. And if we wanted to distribute the 12 over 29, I'll have the vector 24 over 29, 60 over 29. All right. A common application of vectors, again, and we looked at this previously in the other section, is going to be work. So this is a typical diagram that we would use for work. We have some mass or an object, and there's a force that's moving that object, and here we're just talking about horizontal movement. Okay. So that object might move. In a horizontal direction. Again, that's all we're concerned with. So first I would like to talk about the difference between displacement and distance. So if it's a horizontal movement, this distance that we're looking at is actually displacement. It's the straight line distance from the starting to the ending point. However, let's say that we did not have movement along a straight line. So let's say that this is the path of an object. The displacement is the straight line distance from the starting point to the ending point. Okay? That's different than the distance of the curve. So the curve itself, which would be this black line, the distance along the curve is not the displacement. So remember, displacement is just a straight line distance, and in this case we're going to be using a horizontal distance from the starting to the ending point, and that measures how much work is done. So work, we're going to have this constant force. Right now we're not going to talk about a variable force. I think your physics class will talk about that a lot. It's going to be applied to an object producing a displacement, which would just be a horizontal movement. So let's say that the angle between our force vector and the displacement is theta. Then work is simply the dot product formula that we had in the very beginning. So work is going to be the magnitude of force and displacement multiplied times the cosine of theta. Or in other words, it's the dot product between force and displacement. So typically when we talk about work, the units would be in foot-pounds, or it's in newtons, and then the work is going to be in joules. Example 7, we have this wagon, and it's pulled 30 meters along a horizontal sidewalk with a constant force of 10 newtons. So I notice that it's 10 newtons, which tells me that work is going to be in joules, or J. Okay? The angle is 33 degrees above the horizontal. Find the work done by the force. So everything's given. The work is going to be equal to the magnitude of our force vector times the magnitude of the displacement times cosine of theta. And we were told that the force is 10 newtons. So this is going to be 10. I'll leave the units in, N for newtons, times, since it was pulled 30 meters, that would be the displacement, and I'll do 30, M for meters, times cosine of 33 degrees. So if you're putting this in your calculator, just make sure that you're in degrees. So I get approximately, maybe I'll make the squiggly lines, and I'll just round it to a whole number. So the 10 times the 30 times cosine of 33 degrees gives me about 252 Newton meters. And Newton meters is the work in joules, so we're going to use J for joules. Okay, and so another common application that we have deals with objects on an inclined plane. So it's not always us moving an object horizontally, it could be sliding down. Let's look at this object, this box. Maybe it'll be better if I shade it in. This is on this inclined plane. So there's 3 forces actually acting upon this object. The first force that I'm going to look at is the gravitational force. So what it is the object has a weight, and gravity wants to pull it straight down. However, it's on an inclined plane, so there's also these other 2 components. One is the force that wants to have this object slide down the incline. And that's actually a projection of the force vector. We call it the parallel component. Okay? So if we take the projection of our force vector onto a vector v, that would be the parallel component of our force vector F. So what is v? Well, v is, maybe I'll do it. V is this vector that's going along the incline of the plane. So this would be our v. So you imagine a flashlight sort of underneath this time, and we're looking at the shadow of F onto my vector v, and that would form this parallel component of my force vector F. However, this object also has another vector acting upon it. It has another force, and that would be the tendency for the object to want to stick to the inclined plane. That would be the normal component of my force vector. Notice that if I look at the green and the blue shaded, the projection and the normal vector, and we go back to our vector addition with the parallelogram, and I add the normal vector, which will use n, and the projection vector, I add them and I get my force vector. So the force vector is simply the normal vector plus the projection vector. We're going to use this diagram, and we're going to look at a 10-pound block that's resting on an inclined plane. So that's why the force vector here is 0, -10. And we want to find the parallel and the normal vectors. Well, the problem with finding the parallel vector, or the parallel component, is I don't have the vector v. Now remember what I said about projection vectors. It really doesn't matter the length of v. V can be anything. So to make computation simple, we might as well choose v to be a unit vector. So when I compute v, and I need that to find my projection, if I compute v, it's going to take the form of its magnitude times cosine of theta, magnitude times sine of theta. So again, I'm just going back to previous sections when we defined a generic vector in terms of trig functions. I can never speak. So when we look at this vector v, you can look at it as having this theta angle. If we look at v as coming down at 30 degrees, a negative 30 degrees, because we're always doing that in mathematics. What we're always doing is taking problems and moving them to the origin of an axis. Okay? So my vector v, and here I'm just using a magnitude of 1 for v, because might as well, is simply going to be cosine of negative 30 degrees times sine of negative 30 degrees. Again, you could have magnitude of v be any number and we'll still get the same answer because they'll cancel each other out eventually. So might as well just use magnitude of 1. So at negative 30 we have cosine is quadrant 4, that's square root 3 over 2. And then sine would be a negative half. So now that I have a vector, v, I can figure out my parallel component, which would be the projection, right, of my force vector onto that vector v. So the formula is going to be the force vector I'm not going to compute the scalar because I don't have it. So force vector dotted with v, and then I'll go ahead and multiply it by v. That's going to be the force vector dotted with my vector. That's going to be 0. Oops, sorry. Erase. It's a number. That's going to be 0 plus 5. Okay, now, because remember the force vector is 0, -10, and my vector v is square root 3 over 2, -half. So that would give me 5, and then my vector v. Putting this all together, I have 5 square root 3 over 2, comma -5/2. That would be the parallel component, or the projection of f onto v. Okay? So again, parallel component. And it's talking about the parallel component to f. And then the other thing I had to find was the normal vector. So let's go back up here. If we have that our force vector is equal to the normal vector plus the projection vector, and we know the force vector, we know the projection vector, then to find the normal vector, it's simply the force vector minus the projection vector. So that would be 0, -10, minus 5 square root 3 over 2, comma -5/2. Let's see, so that would be a -5 square root 3 over 2, -10 minus a negative, so plus 5/2. That would be a, is that plus 5/2? -15 over 2? So silly, can't do regular math. And then this would give us our normal component. All right, let's look at one more example, and then that will be it for this section. This is going to be another problem with planes. So we have a plane. It makes an angle of 45 degrees with the positive x-axis. Find the parallel and normal components of the vertical force 0, -12. Verify that their sum is f. Okay, so this is just two-dimensional space. And this plane makes an angle of 45 degrees with the positive x-axis. So it inclines with the positive x-axis, and then it makes a 45-degree angle. All right, find the parallel and normal component. The force vector is 0, -12. So again, it really doesn't matter where I draw things. I can draw my force vector coming down here at 0, -12. And then I can move that inclined plane, because again, this is going to be a parallel vector, right? And have this angle of 45 degrees. And then I'll have some normal vector that I need to figure out. This is kind of what our diagram looks like, and this would be our projection. Okay. So first of all, I'm going to use V as a unit vector. And I'm going to describe my vector V as the cosine of, well, magnitude of V is just 1, so it'd be the cosine of, and in this case, since it's coming down, it's a negative 45 degrees. Negative 45 degrees. And then sine of negative 45 degrees. I think I need a new pen. All right, so we're in quadrant 4. Cosine is going to be the square root 2 over 2, positive square root 2 over 2, and sine is negative square root 2 over 2. So we got this vector V, right, coming out here. So my projection vector of my force vector onto my vector V is going to be F dotted with V, so that would be 0, negative 12 times negative square root 2 over 2 would be a plus 6 square root of 2. And then I'm going to multiply that by my vector V. Well, that simplifies nicely to the vector 6, comma negative 6. And that's my parallel component of the projection, yeah, or called the projection. So we were supposed to find parallel and normal. Normal is just going to be my force vector, which is 0, negative 12. And I'm going to subtract my projection vector, 6, comma negative 6. So normal is going to be negative 6. Negative 6. All right. So it also said to verify that the sum is F, which means all I have to do is F equal to 6, negative 6 plus negative 6, negative 6? Yeah, that's 0, negative 12. And we've verified. All right, so that's it for this section.